Hello everyone, and welcome back to a new episode of Advent of Code. It's day 11, and the puzzle was just released this very second, so let's get started. I don't plan to race on this one, but I was eager to get started as soon as possible, so I'm doing it at 9. Okay, very exciting. 9 in my time zone, anyway. Day 11, Hex Ed. Crossing the bridge, you've barely reached the other side of... There was a bridge? I don't remember the bridge. Okay. You've barely reached the other side of the stream when a program comes up to you, clearly in distress. "It's my child process," she says. "He's gotten lost in an infinite grid." Very sad. Fortunately for her, you have plenty of experience with infinite grids. Unfortunately for you, it's a hex grid. The hexagons in this grid are aligned so that they have adjacent things. Yeah, okay, fine, we've seen hexagons before. You have the path the child process took. Starting where he started, you need to determine the fastest number of steps required to reach him. A step means to move from the hex you are in to any adjacent hex. Okay. And we just have to... The fewest number of steps is an infinite grid. There's no, like, obstacles or anything? Okay, what's the catch? I don't know. We'll see. Grab our input here, and let's have a look at it. Okay. Bunch of directions, yep. So how exactly do we wish to... Because, like, hex grids are... They're good for... They have good properties in terms of, like, moving through them sort of makes sense in terms of amount of distance traveled per number of moves. And I think that what we want to do here is sort of like... Well, I remember reading something about a better way to think of hex coordinates. Specifically, that it makes everything much easier if you imagine them as a cube, where the three directions you can move are like north-south is one axis, northwest-southeast is another, and northeast-southwest is the third. And... Right? Like, I remember something like that. I'd be interested to try to figure that out. But also, like, what can we say about this? Like, a sort of obvious thing to try to do is to cancel things out. Like, a north cancels a south. A southeast cancels a northwest. And the other ones cancel too, right? So if you do that, you'll have a final coordinate which is a combination of just three things. Right? Yes. And then I don't know exactly what to do with that. Because you could end up with some northeasts and some southeasts, basically, or some northwests and some southwests. Well, I guess those sort of cancel out kind of in pairs. Like a northwest and a northeast. I see. So it... Okay, I don't think this canceling out approach is very promising. Hex grid as cube coordinates. So here's this article. Hexagonal grids are used in some games, but aren't quite as straightforward or common as square grids. I wrote this guide to the most elegant approaches. Okay. Hexes that we are working with are flat-topped. Isn't that nice and interactive, right? I love it. Okay. Hexagons have 6 edges. Okay. Angles. Yeah, there are 6 wedges. Fine. So what is it that we want to... Like, okay, yes, coordinate systems. Multiple reasonable approaches. I recommend using cube coordinates as primary representation and use something else for map storage or displaying to the user. Fine. Right, so you can offset like this. And then we could have a function move northeast, which based on a coordinate looks at like parity and decides whether to go like this. Well, I guess it maybe does. Maybe you don't need parity to do that, but okay, you could do something like that. Cube coordinates. Ooh, I love this picture. Another way to look at hexagonal grids is to see that there are 3 primary axes, and there's an elegant symmetry. Let's take a cube grid and slice out a diagonal plane. Okay. Wait, what are these? Oh. I guess you can't click on these too fast, huh? The diagram takes a long time. Switch to hexagons. Okay, what does this mean? Alright, well, I don't totally understand that animation, despite having read this article before. Let's take a cube grid and slice out a diagonal plane. Fine. Okay, so when they say slice out, they mean the slice is what we are considering, not that we're removing the slice and considering everything else. The 3 primary axes on the cube grid and how they correspond. The diagonal grid axes correspond to a particular primary hex grid direction. We already have algorithms for cube grids, so cube coordinates lets us use these on hex grids. Okay. Right. So here's the thing. Each direction on the cube grid is a line on the hex grid. Highlight a hex with Z at 0, 1, 2, 3. What does that mean? I don't know what that means. Each direction on the grid, on the hex grid, is a combination of 2 directions on the cube grid. Right, that's what I thought. So like, if you go plus y, you go minus x and minus z at the same time, or something like that, right? Here we go plus y, which involves a minus z but leaving x alone. Or wait, which direction is y? I see, y is this direction. Like through the bisecting lines like this. So there's no such thing as just plus y. This is plus y and leave x, plus y minus z, but leave x alone. I think. The cube coordinates are a reasonable choice for hex grid. Yeah, fine. Coordinate conversions, no. Neighbors, no. Distances, okay. This is more interesting, I think. Each hexagon is a cube in 3D space. Okay. Adjacent hexagons are 1 distance apart in the hex grid, but 2 distance apart in the cube grid. So that's, I think, what I was saying earlier. So, okay, but that's not exactly what I wanted. How do I... All right, hang on. Let me go back to the drawing here. Cube coordinates. So north is plus y minus z. South is plus z minus y. Northwest is plus y minus x. Okay, so we can basically just take this diagram and turn it into a single pattern matching function for computing a delta based on the direction. And then we can just add together those things. All right, let's try that. Okay, so we're just gonna have a really like 3 tuple for coordinates because I think there are some good monoid instances here. Actually, import data dot monoid sum. So I don't know. Let's talk a little bit about monoids here. And what's the deal with sum? First of all, does this compile? Yes. Okay. Actually, 0, 0, 0 as type of chord int. Does that work? No, there's no number. So I'd have to do this if I wanted. Sum is not in scope? Oh. Yeah, okay. So that is possible, but this is not. It doesn't automatically wrap it up in, okay. So why am I writing these sums? It's not really necessary. I think it's maybe sort of overcomplicating things, but what I wanted to do was let x equal this in, oops, I don't need to because I'm in a REPL. Okay, x plus x? No. X and append x. Okay, I guess we have to import that as well. Let's just import everything from data.monoid to be fine, right? Now we don't have x anymore, very funny. Okay, so that does work. Good. So, okay, here's the reason that I'm doing this at all, is suppose that we had this coordinate thing, and we wanted to write, yeah, I don't know, this may not be worth the bother. Really, we're not saving very much, are we? If we wanted to write a function that took, you know, add, say add was a function from chord A and chord A to chord A, we could write add of, and suppose we didn't have these sums here, since the point is why are we putting them in. So let's imagine they weren't there. X, Y, Z, and X prime, Y prime, Z prime equals X plus X prime, Y plus Y prime, Z plus Z prime, right? So like, you would have to write this, which is kind of a lame function. It's not the worst thing in the world, I guess. But this, and this is like a fine approach, but there's sort of a deeper structure here that we're not really taking advantage of, right? Which is, we're just performing this kind of lame operation of adding together point-wise, that is to say for each of the 3 fields in these tuples, we're calling the operation plus. And further, if we wanted to, like, say we have sum takes a list of chord A and produces a single chord A, we could write sum equals fold L add of 0, 0, 0. I guess that would be it, right? So we could do this, and this is how we could add together a list of things. But there's actually sort of like a pattern here that applies to many different data types, and general functions for doing these kinds of operations have already been written for us if we just frame our data in the right way. Specifically, there's this concept of a thing called a monoid. Or, yeah, monoid. That's how you pronounce it. And a monoid is, well, the mathematicians will say it's a slightly different thing from what the Haskellers will say, but we're both sort of talking about the same thing, just framed differently. A monoid is an operation, is a three-tuple, right, is what the mathematicians would say. It's a type and a binary operation between values of that type and an identity element, where the association, the operation must be associative in order to qualify as a monoid. And so there are lots of different things that fit in this category. For example, integers, right? You can say integers are a monoid under the plus operation with an identity of 0. Right, that's a plus is a binary operation taking integers and returning integers, and it has an identity element which is 0, and it's associative. It doesn't matter how you put the parentheses around adding things, it always adds up the same. And so there are a few operations on monoids that are already written for you. A lot of them, in fact. For example, here's a list of monoids, please glue them all together into a single monoid. Is written, which for list of, say, integers means add up this list of integers. Now, the reason that we have to use this weird sum constructor is that there's actually two ways the integers can be a monoid. The other way is if you use the operation multiply and the identity 1. Again, that's a binary operation from integer to integer to integer. And it has an identity element, and it's associative. It doesn't matter where you put the parentheses. And so Haskell, the standard library, numbers do not participate in monoid at all. You can't, there is no instance written for monoid for numbers. Instead, if you want numbers to act like a monoid with adding, you wrap them up in sum. If you want them to act like a monoid with multiplying, you wrap them up in product. And so, actually, let's take so suppose we wrote this, right? We say add 1, add 1. So I'm spending a ton more time here explaining something than I would be if I had just written it, right? And that's on purpose. I know that. And let's say we didn't have that written at all. Now we can say add2 is a function from chord. Well, we really don't even have to write add2, but I'll show you what the so mappend is the name of, is the function which is use the monads addition thing. It's combining operator. Sum2 is just mconcat. And, you know, are we not in Terra mode? Okay. Why does this not compile? No instance for number A. Ah. We have to say this, we have to give it a slightly better type. This is a correct implementation, but it's only possible if the type A is numeric. And we have the same problem up here as well. So by using the sum wrapper that already exists in data.monoid, we can avoid having to write functions like this at all. Because, okay, we explained how numbers are monoids, but we're not even really using numbers here. We're using a tuple, right? A 3-tuple. But actually, 3-tuples can be monoids too, if all the things inside of them are subscribed to the monoid type. And they do that by doing it pairwise, right? If you have, a monoid, if you have a left tuple and a right tuple, and you want to m-append them together, you m-append the first thing in the first tuple with the first thing in the second tuple, and you m-append the second thing in the first tuple with the second thing in the second tuple, and so on. And so all of this kind of boring machinery is already written for us. If we just say, well, I'm not going to store a tuple of ints, I'm going to store a tuple of sums of ints, so that the compiler knows what kind of combining we want to do on these things. We never have to write that at all. And so I think that this is a much clearer way to work with the problem, even though the amount of typing that it saved us is really very little, right? We only saved add1 and sum1. But there are going to be other kinds of things, and I like trying to recognize when these general patterns, like a monoid or a whatever, apply to code that I'm writing. Okay, so we have all this. We don't need these add functions at all because they're already written. We just need a couple of things to deal with these cube grids. Have you guys forgotten about cubes and hexes already, by the way? Because I've been talking about monoids for hours. Okay, so we want a new data type, which is, you know what? We don't need a data type for. I was going to have a type. I think that this would be a better domain model, is to say type dir equals n or south or northeast or northwest or southeast or southwest. I think this would be a good domain model, but I don't know what is the point really. We can just work with the strings that we're given, and I don't see us really needing this, so let's just not. So what I want now is a function which takes a string, the direction to move, and translates it into a coordinate, right? So call it dir. Takes a string and returns a coord of int. Yes, that seems fine. And we can just write dir of n equals, now I'll go consult this map. To go north, you add 1 to y and subtract 1 from z. Okay, I don't want to have to write sum 18 times. So what we're going to do is say dir of s equals sum x, sum y, sum z, where x, y, z, equals case s of, and now we can do the pattern matching. This is a weird place to put, to indent the line to, Emacs. Man, I don't know. Okay. So for north, we are producing a 0, 1, minus 1, minus 1. South is going to be the opposite of that, of course. 0, minus 1, 1. Northeast is increment x and decrement z. So southwest must be the opposite of that. Minus 1, 0, 1. Finally, northwest is increment y, decrement x. Oops. Hang on, did I transcribe the northeast correctly? Northeast was increment x, decrement z. Yes, I got that right. Okay, so northwest is increment y, decrement x. northeast is the opposite of that. Okay. That looks about right. Why is this being underlined or highlighted? Patterns redundant. Oh, thank you for reminding me that should say southeast. That would have been fun. I guess we would have caught it pretty quickly. A non-exhaustive pattern match would have given it away. So now, part one is going to be very simple. Part one is a list of string to int. Part one, we can probably just write this as some function compositions, right? There's some monoid function for like mapping and also concatenating a thing, isn't there? I can't even spell monoid. Here we are in monoid. Mappend, mconcat, yes, very nice. Yeah, there's all these type wrappers, which is great. First, last. I guess not. Okay, well, that's life. No big deal. Okay, so part one is let's see. Add, I guess we'll say, add of mconcat, add composed with mconcat, composed with map dir, where add of some x, some y, some z equals x plus y plus z. Great, that type checks. So now all we need to do is parse the input. And I seem to recall that it is a single line comma separated. So we will write this. And let's just go borrow split from our day 10. Oops, wrong function, wrong file. That's the compiled executable. I knew I should have generalized the split. I thought I wrote a general split and then it like didn't look as nice, so I took it back out. Okay. Okay, this split is a function from A to bool and a list of A to a list of list of A? Yeah, that sounds right. Split PS. Oh, we don't need that. Alright, I guess I don't want this stupid general one, huh? Because I have commas anyway. Alright, I don't... What is the type? Go split, please. Oh, wait, I should get used to using Intero. That's the type of split. String to list of string. Split is a function of string to list of string. Okay. Fine. We shouldn't really call these num. We should like call it x or something. Okay. Part 1, Part 2, split headlines. Okay, that seems promising. Let's see what happens. We call stack run VHC of source main fed input.txt. 0. Okay, not very promising. I don't think that's right at all. Why? There's a function in data.list, right? That, how do I get to data.list? I want a scan. I think. I kind of want a scan L. Except I'm trying to debug what are the intermediate values here, and a scan is what it's going to tell me. Instead of using mconcat. Well, I guess first of all what we could do is just write show me what we got as the result of splitting. Like, I don't think that's going to be very interesting, but I suppose we should check. Yeah, that looks correct. A list of strings, and they're all quite reasonable. Okay. So what's the deal up here then? Let's take away the type information for part 1 so that I can just like make this return whatever I want. Let's just look at the output of concatenating together and see where we wound up. Oh, we wound up at like interesting. So 764 and minus 764. So these actually do add up. It wasn't just that we were doing nothing somehow. We took a bunch of operations that went right back to the center. Okay, I guess I'll try 0. Oh, you guys didn't see that. Here it is. I just changed the type of add here to, or I use identity instead of add to see like what is the final coordinates we arrived at, and they're actually like some non-zero coordinates. I don't know. I'll try 0, I guess. That's not the right answer. Okay. Well, that's fair. I mean, I guess the answer is too low. Oh, wait a minute. So, of course. Because anytime we move at all, we're increasing one direction by 1 and decreasing another by 1. The sum of these is always 0. You can't just add these numbers together to get a distance. We were supposed to have read that in the document here about distances, and I got that far and then went back because I didn't understand some other stuff. Distances. I see. So it's for each pair of coordinates, add to get, or subtract them, but get the absolute value, and divide the total by 2. An equivalent way is noting one of the 3 coordinates must be the sum of the other 2, and then pick that as the distance. Interesting. Okay. We can write that. So let's write a function called distance that takes a right? This is, of course, we're being more general than we have to. Our coordinates are always of type integer. But again, I like to try to be general about things when I can. And this coordinate type, in principle, could hold any kind of numeric thing, right? So our distance computation will work for anything that is numeric as long as it is also ordered. There's a way to compare values to see which one is the biggest. So let's see. Dist of sum x sum y sum z equals maximum of diffs where diffs equals for a in equals what? Absolute value of a minus b for a in amounts and b in amounts, and amounts is equal to just the list x, y, z. So this will include like x minus x and see which is the biggest, but that's fine because if the greatest absolute value is 0, then like it doesn't really matter, right? Because that means all the coordinates are 0, and so 0 is the right answer after all. So instead of add, it should be dist here. Now when we run this, we get an actual number. A non-zero, useful-looking number. That's not the right answer also. Very funny. Why? Did I misunderstand the... I did this wrong again. I computed the wrong distance. I don't know what I computed is a mathematical quantity with no meaning. I'm supposed to be computing the distance between two points, not between like two coordinates within the same point, which makes no sense. So I need to introduce a 0, like compare this to the origin where we started, right? So and since subtracting something from 0 and taking the absolute value is like boring, I can just say must be the sum of the other two. Yeah, so I can actually just say maximum of x, y, z. Right? And we get a new number. Let's just try putting in more numbers and see what happens. Okay, so is this correct? This doesn't look right, actually. Oh, I see. Right, they were saying this number must be... one of the numbers must be the sum of the other two. And indeed, 520... no. Is 521 the sum of these negative things? One of the three coordinates must be the sum of the other two. But that doesn't seem to be true for our thing, right? But also, how did the function that I wrote come up with this answer? Oh, because I was supposed to have checked the absolute value. Okay. And now we'll get the largest one, 764. And it is the sum of the other two, modulo being negative, right? So I think that this is actually a reasonable candidate for our answer. That's the right answer. Okay, great. So let's commit that, and then we'll get started on part 2. Did I commit anything I didn't want to here? No, this looks right. All right, part 2, day 11. How many steps away is the furthest he ever got from his starting position? Well, this is just great because it's really easy for us. We can just, instead of using mconcat, we can use like scanl of mappend, and we'll have a list of all the places he's ever been. You guys should look at this screen, please. Great. Part 2 is maximum.mapdist.scanl mappend of... Do I have a good origin anywhere? Oh, I don't need it. It's empty. Of course, silly. That's why the mconcat thing worked. Empty is the identity. So the identity for a three-dimensional coordinate of sums is just 3 zeros. And Haskell knows this, and we don't have to do anything. Yeah? Why is this not type checking here? It returns... Alright, well, whenever you get a weirdo type error, it's because you didn't put type annotation somewhere, and Haskell has inferred the wrong thing. So let's say what type I expect this to have. Dist. Well, okay, whatever. Part 2 should be of type list of string to int. Now, why is this upset? Maximum map what? Oh, I forgot the map dir at the end. There we go. $1532. That seems, I don't know, plausible. Can't copy correctly. There we go. That's the right answer. Great. So that was kind of fun. I got to play around with cube coordinates for hexes. I don't totally understand exactly how it all works or why, but I don't know. It was good that I had heard that before and knew where to look up like how it works, like the right words to look for. I don't know. Obviously I could have done it without that, but hex coordinate systems are a bit like wonky to do by hand, and this cube thing made it relatively straightforward, I think. Anyway, let's just add in. Oh, whoops! There's something I changed in the previous puzzle, I guess. Yeah, look at that. The most minimal change at all. Just implement part 2, don't touch anything else. Day 11, part 2. And now let's get Kami? No. Let's, what is left over in day 10? Oh, I changed, yes, when I was explaining my solution to this, I said here's a better way to do that. Okay, fine. Git commit -m day 10 slight cleanup. Cleanup. And we'll just put that back with the day 10 changes. Something like that about right? Yeah. Okay, cool. That's it for today. Hope you guys enjoyed. Thanks for watching, and I will see you next time.